here let's start from the second part. Okay, first one is fine, right? I think we discussed that. All right. So in the second one, let me take out the question as well. Yeah. So we'll first plot the this thing. Okay, just check. This is the value, right? 36, 28, 44. Right? It has to be very specific for your given number, right? Huh. All right, all right. 844. All right. Right. So we get this plot as a root locus for this given number, and they say that we have to find out something from this, and we need to look at the stability as well, right? Okay. So it says, just a second, let me remove this. Okay, there's a mouse on the root locus screen uh, plot to determine the limiting value of Kp of the system for stability. So that means uh, I know that as the as I am moving the this thing, right, we can see that uh, the gain and the other values change, right? Right, as I am moving, you can see that, right? This is changing, correct? All the values we can see, and the limiting value comes somewhere here, right? But I have to make the x-axis value 0. That is pole value. What do you see here, right? This should be perfectly 0. That, yeah, that's the one thing. Now you see it is on the positive side, which means it is actually unstable. I have to make it as close to 0 as possible. 0, this is negative 0.8. Yeah, somewhat like this. Okay, maybe this is the closest one which we can get, but I would like to keep it one more negative side. Yeah, maybe still reduce. So it has to be 0 on this side. Okay, that's what I'm expecting. Point 0, maybe. Okay, so this is assuming this to be 0. Now you can see that what's the value of the Kp? That should be the gain. Okay, so I think I'll try to come much closer, because when I ran earlier, I got a different answer, 31 point something. Yeah, you have to do it. Huh. Okay, okay. Hmm. Hmm. Okay, okay. So pretty much closer. All right. Uh, right, and so that was a first part of the question. Anyway, we have to prove this. There is a calculation to be done in the same question. So this is what we need to check, I guess, for the first part. So use the mouse on the root locus to get the limiting value of Kp. Next is calculate by this value by hand using the RH criteria, right? So I'll show you that now. So let's move on to the RH thing. Okay, so this is what, right? So you can see that the equation we can directly get from here, right? In the okay, they themselves have shown what is the value of equation. I'll just we can get it from the MATLAB itself, right? So the equation for G we have, right? I think we have it on the screen, right? So I think we have the, sorry, this is not the, um, this one, this is a G, right? 0.91 this thing. I have to multiply that with the equation, right? So I'll show you the calculation. So Kp into G is your equation, right? That this is the equation. H is there is a feedback which is equal to 1, so you can see that that's why I have written H of S equal to 1, right? And write the total characteristic equation needed to solve any question that is based on RH will be, right, 1 plus GH equal to 0. Okay, so we write that. So we can see that anyway, as you told, the denominator will get plus 1, right? Because this is GH, right? Plus 1 on the left side. I'll take the denominator to other side, multiply that with this. And directly I wrote therefore, this is the characteristic equation. It's okay, right? So I actually skipped the step. And coming to the root array, right? We have, right? So the highest power is S cube. So this is the RH table, right? So S cube, S square will fill the this thing, and we calculate the values, right? And I think the table should be pretty straightforward for you. Okay. So directly I'll go for the solution, right? Since the first two entries in this column, they are positive, I'm expecting all the others to be positive, so that this becomes a stable system, right? So that's why the limiting a value of kp comes into picture. Anything other than that kp value, it becomes unstable, right? So this is positive, means k has to be more than 0. That's why this point comes into picture. Okay, so kp should be greater than 0. Any value lesser than 0 makes it unstable, right? So I come to know that k greater than 0 from here. And also in order to solve the other, the bigger value, we have to solve this. That's what I have done over here. So when I solve that, I got kp should be 31.6, right? We can see that the same value is in the graph, correct? The gain equal to 31.6, right? So in this we can see the same thing. Gain equal to 31. That's how you verify. Okay, so that's done. Let's move further. The next question. Do you have any doubt with that? Okay, so 2.1 is done. 2.2 says include the printout, verify the plot, explain the characteristics. Verify the plot in the sense you have to check that where are the roots. Are the roots fine? We already have the roots, I guess, right? The poles of the system, right? So we have to verify that whenever you have two poles on the real axis, right? There will be a root locus coming towards each other. That's happening. The blue and the green color. The, and at somewhere at the center, you should have a break away point. It's breaking away, and we can see that it will be traveling, since there are three branches, right? Each should be right. I think 120. How many? What's the degree? We calculate a phi value for this graph, right? Root locus. If you remember the procedure, or even you can actually solve this thing, because anyway there is no restriction in the way of writing the answer, right? You can actually completely solve. I didn't solve this. Maybe if required, you tell me, I can even solve that step by step procedure. Okay, so three things to be identified. First point is that number of branches, that is equal to number of unmatched poles. So how many? Three in this case. There are three poles and three are not matched, right? There is no zero to match a any given pole, right? So that means three branches, all the three branches going to infinity. Yes, we can see here, right? There are three branches going to infinity. That's the first verification. Step number two in the verification will be, right, where is, which part will have real, which part of the root locus will lie on the x-axis, right? So which are the part? So we have three poles. So starting from the rightmost, as soon as I cross the first, that is the zero, sorry, pole at a s equal to 0, the origin. As soon as I cross, there is one pole on the right side, which means odd. Whenever you have odd number, you have to get the root locus on the x-axis, if you remember. So that's why I'm getting a root locus here, right, until here. So as I cross this, I get here. That's the blue and the green. As soon as I cross this point, you can see how many are there on the right side. The count becomes even number. So no pole, right? As soon as I cross this until infinity, right? It is odd only. So you have the red which is going till infinity. This is the next step. We verify that it's happening here. Then we see that, okay, there are, okay, one of the branches directly going to infinity. There are two more branches expected to go to infinity. Now we know that whenever there is unmatched poles going to infinity, it will be through the help of asymptotes. So asymptotes has that actually has two calculation, right? One is the centroid. Somewhere here it will come, right, when we manually calculate, right? From there I draw three lines, one like this and one more like this. Yeah, one more like this. Correct. One more like this. So there will be angle of asymptote which you need to calculate. That's what I told. Some phi will come into picture. Phi 1, phi 2, phi 3. So it will be 60, 180 and 2 something. Okay. Uh, okay. 60 plus 180 plus 120 to that. Okay. All right. So you get three these things. All right. Something like minus 60. All right. That's from this side. Right, three angles you get, and you have to also find what is called as the breakaway point. So the breakaway point is something uh, related to this point. I can actually move the mouse pointer over there. You can see that somewhere here you should, okay, this should be only the real number, okay, no imaginary part. I think I moved the thing slightly. Yeah, something like minus 4 looks like, okay, there is a value of minus 4. Something like this is what is expected when you solve for the breakaway point. I should get a number, real number. Yeah, so solve dk by ds equal to 0. Okay, write a equation for k and differentiate dk by ds. Get the dk by ds, equate it to 0. So yeah, and solve. Then you get whatever is the root of the equation. You may get multiple roots. Select the appropriate one from that. Okay, so you get lies on the, whichever sorry, whichever is present in the range. Like I'm expecting, so if I get a point like say 18 and 4, you have to select a 4 because 4 is, yeah, yes. Okay, so can you do that part? uh, okay, let me know if you have a doubt. I will help you out in that. Okay, so that's a 2.2, I guess. Right, verify. Okay, let's move further. From the root locus, determine whether both the design specifications can be simultaneously possible to meet. Yes, so the design specifications, I think one is the overshoot should be less than 10% and less than 0.5. Right, T 0.5. Correct. So TP cannot be directly measured over there on this graph as we have seen now. So only option I have here on this graph is to measure the zeta value, correct? Because these lines are corresponding to, we can say that, right? These lines are the zeta values, right? Zeta is 1.99, 0.96, and so on, right? So if you remember, corresponding to TP, I can actually calculate the omega d, and from the omega d, you can actually go back to the zeta value. That's the one thing. and the OS is directly visible, right? Whenever I click somewhere, I can see that what is the overshoot, right? So they say that overshoot should be less than 10%. So you keep it, you bring this down such a way that it reaches somewhere around 10, very close to 10. Yeah, maybe. Yeah. So 10.6, 10.2, 9.78. Yes, yes. So corresponding to that value of overshoot, right? You can definitely calculate a zeta value, correct? Maybe I'm not able to tell. Yes, yes, yes. When it is 10, I am expecting it to match. Okay. Try to make it exactly 10, then only we get the proper 0.59, I guess, right? Okay. So just see to that it comes as closer as possible. That's all. Okay. Right. So they asked, okay, this is the first part, that is overshoot should be less than 10%. Now you have to say that calculate omega d from here and check, right, what should be the omega d corresponding to TP less than 0.5. I think 6.28, right? Because we are dividing pi by omega d to get the TP. So pi 3.14 divided by zero point 0.5 is multiplying by 2. So 6.28, right? So my question was, what is omega d for TP less than zero point 0.5? You had that in 1.2 question, answered 1.2. Huh. Yeah, 2 pi, 6.28 something. Right. Okay. So 6.28. Where do you get the omega d? Omega d is the imaginary part of your 4. Okay. Do you remember one equation? The what you call real part is zeta into omega n. Correct. So pole is equal. Huh, correct. So zeta omega n plus or minus j times, right? Omega n into root of 1 minus zeta square. Right. So that means you can actually verify from here also. I have a 3.38 as a zeta omega n, right? And zeta is equal to 5.76. Sorry, omega n equal to 5.76. So divide 3.38 by 5.76. How much you get? 3.38. Yes. Yeah, that's the zeta, right? We have same thing. So, 5.9. Right. I'll show you the one which I calculated. So you can see here, this is what I got. I had saved that image. So omega n from this, I can see that 5.74, 5.74. And you can see zeta omega n is 3.39 when I got earlier, right? So divide that. So you that you can, here I got actually overshoot equal to 10, right? Exactly, I kept somehow, it reached 10 in this diagram. So you can see that zeta comes to be 0.59, which is matching, and omega d is 4.63, right? Which is well inside our marginal value. Omega d, right? Value expected was something like 6 point something, right? Like that, right? So now we have one situation over here. The question says that is it possible to match your requirement? The design requirement, can you match? So what should be the answer? So you're okay with the what I huh? No, that's right. So you just have to remember. Let's go back to the question. OS, that is a overshoot should be less than 10%. Okay, that means let's this is overshoot is 10%. We got what you can see. Less than 10% means I have to come down, right? So my region of region corresponding to overshoot less than 10% lies between, so axis 0, that is this 0, or in terms of zeta you can measure it 1 till zero point 0.6, right? This region. So I have to shade this region for, right, obtaining that. But I have another part, right? They have another question to met, that is TP less than or equal to zero point 0.5 means what is the minimum value of omega d? 6.28, right? So right, it should, the minimum value itself is 6 point something. It should be more than that. So when I move my cursor to reach the 6.28, I go outside my this region, the right, I have to move upwards to match that. So I'll show you. So this is what is the condition, right? I have to move upwards to match 6 point something. Yeah, 6.28 maybe. This is 6.2, okay, 4 or 6.3. Now you see, right? Overshoot is increased. Overshoot is 23.4, which is, so that means I am not able to meet. So the question says here, are you able to meet both the required conditions using this? So the answer is no. Okay, from the root locus, determine whether both the design specifications, that is 2.3. Okay, question number. First part of the question says that, are you able to meet? So answer is no, because you can save both these and you can put it over, right? Both plots, both screenshots you can take and save. Next is show the area where the dominant poles must lie in order to meet the both specifications on the root locus path. One is less than this side, that is zero point 0.6, right? Uh, yes, yes, less than 10%, correct. So corresponding to that, whichever area you get, you mark that. Okay. Show the area where the dominant force. Yes, yes, that's, yes. So yes, yes, or more. So more area you will mark. So higher area. Okay. So both simultaneously matching is not possible. Individually you can match. Okay. Right. So either you will be able to mark less than 10% area, otherwise you will be able to mark those points, right? Which corresponds to this is zero point 0.4 and higher one. Okay. Damping should be at least 0.441, right? Or more to visualize that that's happening. Correct? I'll just come back. So right now you can see that damping. Now the first point you understood, right? The 10 value, lesser than 10. So somewhere here, maybe this is 10. So that means this is the point. 10 means it is zeta value comes to be 0.59, correct? So every value that is lesser than zero point 0.6 will be covered. So this area, right? This horizontal, this area. This is the complete area which we are talking about. Okay, that's one thing. Only that is matching less than 10% condition. Yeah, right? Yes, that will act as one of the boundaries. Okay, right. So that's one part. That area can be considered as such. Okay, right. So that means, right, whatever is the common area between both of them will be this case, right? Will be the required answer, right? So then moving on to the next part of the question. Okay, it says record the value of Kp at a minimum required omega d. Record the poles at this point, determine the zeta and the predicted overshoot. Right? In a sense, I need to record the value of Kp at the minimum required omega d. So Kp at minimum required omega d, in the sense I have to come back to the same graph and 6.28. Right. So select something in some number which is very close to 6.28. Yeah, I think also slightly more. 6.28, maybe 6.26 is what I am coming closer. Right. At this point, you need to identify the Kp value, which is the gain. You can see that gain equal to 6.58. Right, and the poles, right, you require poles, record the poles, right, pole. So minus 2.93 plus 6.26, minus 2 plus, sorry, minus 2.93 plus or minus j 6.26, both conjugate, right? So you get two of them. Determine the zeta. Zeta can be seen over there, right? 0.424. And what's the next one? Predict overshoot, 22.9. Overshoot, you can see here, right? So these are the values which they are asking us to record from this. That's the okay. Next, we directly go to the next part of the code. They say that do that. So move on to the next one. So this is done. We'll move to this part. So you see that they are asking you take a value of Kp and solve. So initially I start with the Kp equal to 4. So randomly I chosen. So anyway, 4 is what we get lesser than, we have it with lesser than this, right? So I thought 4 is a one value. Anyway, value has not been specified in the whole question. What Kp you need to take, right? Later on I understood what we are supposed to take. Okay, so what I did, I'll show you. Okay. So this is not required. I'll close. So now nothing, no change, no change. Everything as it is. You can see only they say that after that 2.3 question, they say that to read a value required for Kp from the this thing. So I have written only this value. Right, you can see Kp equal to 4 is the additional line. Then T is equal to feedback. This generates a feedback system, right? Which is Kp into G will be on your, as the input comes, get it multiplied with Kp into G. So after the output of G, you take a feedback, give it back to the input. Okay, so that's the feedback system. It generates a feedback. See, the H of S equal to assumed as 1. So this is G of S, this is H of S. So unity feedback system is what they are creating here. Okay, that's what feedback does. Yeah, sure, sure. Please take your time. Yes, yes, yes. We start with 5 initially. 2.3 is over. After that, they have given some sentences to read, right? So enter the required value of Kp. Kp is what you have to enter. Okay, any value. Enter the required value of Kp. No, no, actually we have to, they have not specified, but we have to do something. But initially I never knew that, okay, I have to do something like this. After solving for the Kp equal to 5, then I came to know something. Okay, I'll update you in the same way. Okay, let's see, let's solve for Kp equal to 5 first. Okay, randomly I took Kp 5, right? From the graph, I thought, okay, let the computation be easy, and I took 5. Okay, right. So you generate everything as given, right? T is equal to uh, feedback of Kp into G, right? We get, see, when I run this, you can see here, I'm getting this. this one. T is equal to, from here I'm getting the answer. Because this T, then the damping, then the step. All the three we got. So this is the transfer function for T is equal to G divided by 1 plus GH. Whenever I did that, I'm getting this. Okay, then they say calculate this damping ratio and the pole, right? So we this is the answer. Damping ratio and the natural. All of them will be given by the one single command, damp of T. Okay, it says what are the poles, right? What is the damping at each pole? What are the natural frequencies corresponding to those poles? Okay, so these things we can see over here, right? So the value is 3 plus sorry minus 3.25 plus or minus j 5.17. This is the root which we have to get, uh, complex root. This is the real root, 22.3, because it is E01. Okay, so into 10, right? So we get minus 22.333 something, right? When we manually calculate, but this is what they say. MATLAB says that, okay, 22.3. So similarly, you get the damping. Always damping at real value is 1, so you don't have to do this. You have to get this value, right? 5.33 is what we are expecting. So E minus 1, so this is 0.533. Okay, like that. We have this thing. So next part, we'll move to the. Okay, from the graph, you have to identify, measure the OS and TP according to this question, right? So MP is the highest point on the graph, okay? And corresponding to that, whatever is the time is the TP, right? So maximum. So you can, correct. So as I move on, I can see that the highest point is 1.13, and the first value you get for 1.1, 0.616. You can see the graph, right? Oh, sorry, it's not coming. Just a second. I'll run 1 second. Yeah. Now you move cursor over here, just to see that 1.13. That's the highest, but it stays there for a longer time. You need to record the first interval, first instant when it reaches that, around something like this, 0.616 maybe. That's the point. That's the time taken by this system to reach its highest point from t equal to 0. So that is equal to 1.13. So you see that we got 13% overshoot in this case. So OS is equal to 13%, and TP is equal to 0.616, right? So that's the measure part, right? Given in this question. So 2.3 is complete. Okay, you are also getting the similar answer. You have any doubt? Hmm. No, 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 no. That this is what is give any KP as per this question. We understood that give any KP. So for yeah, we have given any KP, and we have taken KP equal to 5. For this, anyway, we'll verify this. So the next question says you got something from this graph, right? Prove that. That's the next question. 2.4 is asking us to prove this. So manually calculate, and for a taken KP value equal to 5, show that this is the proper answer. Manually do the calculation. Okay, so initially I did for this, but later on I have to understand that, okay, if I want a stable system, what I should do, right? Later on we'll change this KPI and we'll calculate once. Okay, but I'll show you the fundamental calculation for whatever KP value given. How do we proceed? Okay, so this is okay for you? Huh. Ah, yeah. Later on, maybe we have to go for a stability case, right? So, but the fundamentals of calculation remain same irrespective of what KP it is. Okay, right. So, so far this is good. Let's move further. Huh. I have taken 5, right? Anyway, I'll show the even the manual calculation for kp equal to 5, right? So it, but in order to answer this, maybe you can take up a kp value which is satisfying our condition of less than 10%, right? And you can proceed. Okay, I never knew. Correct. I never knew that. Okay, that has to be taken first. Perfect. Perfect. Okay. So anyway, initially I took this and I calculated. Then I went to question 2.4, the details. Then I understood that okay, I should have even taken for the other, the safer value, which is less than 10% of this. But I got it. I just have to prove that okay. I took KP equal to 5 and I'm getting 0.616 as the TP and 13% as overshoot. Okay, this I need to prove, but later on I'll run the same code with KP equal to maybe 4. Then I get a what do you call this amplitude is 1.08, which is lesser than our threshold, right? 10%. So that is just 8%. Then I need to do this once again, the whole calculation. That's all. Okay. Right. I'll move to the calculation part. So I keep this as my reference. I think I have saved that somewhere. Just yeah, I have it. So this is the graph, right? You can see, right? Kp equal to 5, I have taken. And when Kp is equal to 5, right? This is what is the graph. And from here, I calculated that Mp is equal to 1.13. So overshoot above 100, how much it exceeds is overshoot. So it's at 13%. So, or maybe 0.609. So sorry, I wrote wrong. I changed the TP. That was some initial value, initial graph I collected. So let me write the TP. So that comes to be 609, 0.609 seconds. All right, now we'll move to the calculation part. So write the transfer function, right? This again, you can actually solve. The G is given, K is given. You just have to write the transfer function is equal to G divided by the Kp into G divided by 1 plus Kpg, right? Yeah, when you solve this, you get this, right? The same thing you can even see in the MATLAB screen, right? Command window. It shows the similar one, very close to that. Okay, so just let's verify that once, whether we are writing the same thing. Yeah, this one. The T is equal to 4.563 divided by this one, this part. Okay, now we have that. So right. So in which in this from this particular uh, transfer function, I need to extract the denominator and equate it to 0, right? That gives you this uh, system poles, right? So when we solve, uh, I directly applied calculator to solve this. I got these two roots, right? So sorry, three roots: minus 22.3327, minus 3.25, plus or minus j this number. Okay, so I will go back to MATLAB to verify whether that is right. So you check that MATLAB already said that what are the poles, simply compare it with them. So minus 3.25 plus 5.17, minus 3.25 minus j 5.17, plus or minus 5.17. Okay, right. So we are getting very closer to that. Okay, minus 3.25 plus or minus j 5.17 something. Okay. Okay, that's the first part. Then I need to calculate. I have to go till the calculation of the overshoot and the TP, correct? So for that, we need to do some calculation like this. So for a third order system, right? This is the equation. right? Anyway, this is a third order equation. So this is the third order equation. So for a third order equation, in order to in order to compare this with something standard, I need to have a s cube here. I don't want the term multiplier. So what I do, I divide this whole equation by 0.005475. Okay, so when I do that, I get this as the is the same equation represented in a different format. Okay, so you see coefficients change. I need one here. That's why I did this. I needed a one here, one into s cube. Are you okay? Right. Okay. Now this is the standard. See, if you have a second order system, what do you compare? You always compare the denominator with s square plus 2 zeta omega n s plus omega n square. That's the second order standard equation. Similarly, the third order standard equation is this. Okay. So here it is something like s cube plus 2 zeta omega n plus p. P is the real, p is a pole value, magnitude of the pole. That is equal to 22.33. But anyway, I'll prove that. It comes that only. Ah, yes, yes, yes. P I will calculate from this equation. I'll calculate P and then I'll substitute back. I don't put this. Anyway, I know that P is equal to this as from the theory part, but we need to prove that mathematically over here. Okay. Yes, yes, yes. So keep this and compare, right? I'll compare that this 28.84 is equal to this, right? 2 zeta omega n plus p. So let's submit here this one. So I have equated that over here, both of them, and I calculated the zeta omega n part as a equation, which is equation 1. All right. Similarly, compare the second part, 182 point this, right, should be equal to the omega n square plus 2 zeta omega n p part, right? That's here. From where I calculated the only I kept omega n square on one side, moved everything to other side, so that in a later stage in this I can actually substitute everything back. So this is equal to omega n square, from where you got this one, sorry, this I didn't mention. So this you can compare with the p into omega n square, right? That's the last part, constant. 833.42 is equal to this, according to. So keep only omega n square on one side. So omega n square becomes equal to this. So now substitute it. Yeah, yeah. That's by dividing the whole equation by this number. Point 0.005475. Throughout the equation you divide. Then you see it cancels. So I have a 1 into s cube. Then this number becomes this point 1579 divided by 0.005475 equal to 28.84. Okay, same thing repeats. There is a 1 here, 1 into s. So 1 divided by 0.005475 gives you 182 point something. Okay, and so on. 4.563 divided by that gives you, right, 33 point this. This is the standard form because I need something like this to compare. Are you okay? Huh. No issue. No issue. That's fine. So then the equation 1 and these part, are you fine with this? This still here? That's fine. So then I put every values I got in this equation because I have omega n square. I can write it as 833 point this by p, that is here. Okay, omega n square is equal to this one. And also I have the 2 into zeta omega n. Zeta omega n is calculated in equation 1. Substitute that. So 2 into zeta omega n into p. Right. So I have the complete equation containing only p. One equation, one unknown, solve, you get 22.33. So that's the same value which I mentioned earlier, right? I have to take the magnitude of this. So P is equal to that. Once you have P like that, I can actually calculate the omega n. You can see this equation. So substitute P, you get 6.10, right? That's the omega n. Then zeta is once again, we know that zeta omega n equal to this equation number one, right? Simply move the omega n to the other side in the denominator. So zeta is equal to 28.84 minus p divided by 2 omega n. So you see this 28 point this minus this by 2 omega n. You got 0.53. Then we can calculate the OS and this, right? So because I needed a zeta, right? So OS out, this is equal to, yes, 1 minus zeta squared. So you get 13.84. Now you go back to the MATLAB window to verify that answer. So now you see I got amplitude is equal to 1.13. No, I think I have it here only, right? So this one, you can see 1.13. So out of which 100 you have to remove from that. So overshoot is 13%. And now my answer says that 13.84%, right? Okay, similarly calculate the TP, pi by omega d, but I have not calculated omega d. I substitute omega in root of 1 minus zeta square. Substitute 0.607. So we'll see TP I got as 0.609, right? So pretty much closer. So this is what is the calculation required. So next I understood that, okay, I need to bring the what do you call overshoot lesser than 10%, right? So now anyway, I couldn't do the whole calculation, but I run the code for t equal to 4. Sorry, kp equal to 4 once now. So I'll make this only make the change tp equal to, sorry, kp equal to 4 in this. So what happens? Our equation will change. That's all. The t equation, whatever t we have, right? T of s, that will change. So you see, got a new value, new t now. Here you can see t is equal to 3.65 plus something divided by a new characteristic equation, right? Now, whatever step I did for kp equal to 5 has to be repeated to prove this, right? What you need to prove is move this. So look at the highest value what it takes. It's 1.08, I guess. Correct? Highest value amplitude is 1.08, which is 8%. Correct? Lesser than, well less than the required this thing. Required value is 10%, so 1.1. Or else what you can do is you can keep changing the KP so that it reaches exactly 10%. That's also fine because they never mentioned what has to be done in the problem, in this problem, right? Take any value of KP is what is the statement. We can take anything, even the 5 should work because they just told that, okay, take any value of kp and prove that, okay, whatever the MATLAB gives you, it matches with your manual calculation. That's what you need to prove, but you decide whether to put a value within the range or something. Okay, so both of them, it cannot satisfy. That's the answer. Ultimate answer is that one of them you can meet. Okay, either the what you call, yes, yes, can you meet both the condition? Correct. Hmm. Both condition cannot be met here, right? One of them definitely, right? Either you meet less than 10%, wherein your TP will be more than this, right? You can see, right? Whenever the overshoot is less than 10%, what is the time? Time is 0.7, which is not possible, right? It should be less than 0.5. But if you take maybe you can solve two things now. Maybe that makes it more clear, right? If you try to select the value of kp such a way that the time is within the range, okay, time is less than 0.5, you do the calculation, you show that amplitude does not match. Next one is this itself, the kp value equal to 4, right, which shows that amplitude is less than required value but the time is exceeding. Maybe that's the proper answer. No, no. One problem you have, one value is fixed, kp equal to 4, right? This satisfies your amplitude condition. Amplitude is less than 10%. Now, what you are seeing here, okay? Satisfy the amplitude. Okay. When we do that, you can see that amplitude is well within the required this thing, but the time has exceeded. Time is required is zero point 0.5, but you see 0.77. So your answer is yes, one of them is satisfied, other one is not satisfying. Next, you take another KP, not 5. 5 is not satisfying both. Okay, maybe more than 6 or 7 you take, right? And verify that time will satisfy. Time comes less than zero point 0.5. Okay, wherein you will see that amplitude exceeding 20%, 23%, whatever, right? So there you will give again you will solve you same way whatever we did so far. Same mathematics you will do, and you will give an answer saying that in this case where kp equal to say 7, right? The time is less than zero point 0.5, which is the required condition, but amplitude is 1.23 or 1.4, whatever it comes, which is not satisfied. So your ultimate conclusion is that using the proportional whatever design, this kp is called as a proportional constant, right? So using this only the proportional design, right, we cannot meet both the conditions. So that will be your final answer for that question. Whether you can meet both of them is the question, right? So compare the overshoot. So that's the last part of the 2.4 overshoot time with the predicted value on the root locus. That's what I have to compare. I have to get, you have to solve until you get the overshoot and this, irrespective of whatever value we take. So this calculation, whatever. So, so this question, what we have, this solution we have given, right? This has to be done for two different cases where, right? In this case, you can see none of them is satisfied. So that's why neglect the 5. Just take the method, okay, how to solve and solve with the two values. Neglect this because I, without knowing, I started solving. After solving only, I could come to know that okay, this is what I'm supposed to. Yeah, one value is 4, and select another value such that the time comes within the this thing. Okay, time is less than zero point 0.5. You have to you simply have to run this again and again, right? So MATLAB, yeah. So that keep changing the value kp in the MATLAB function, and verify the step response graph you get, right? Wherever the time comes lesser than zero point 0.5, hold on to that. That kp you take. Okay, so that will be the yes, yes. So that is the other value of kp which you should take. One is 4 fixed. Okay, other value you find out satisfying the time condition. Time should come less than zero point 0.5. Okay, so for which definitely you will see that amplitude will be not satisfying. Amplitude will go beyond 1.1, more than, anyway, now itself it is 1.13, zero point 0.6. So when it comes lesser than zero point 0.5, this will be overshooting more than say 25 or something, 1.25, 1.3, something you will get, right? But anyway, ultimately we need to prove that okay, whatever comes on the screen, it is calculating, this calculation matches with our manual calculation like this. So that has to be shown. That's all right. So that's the complete part. I could do only till here. Maybe I'll try, if I try to find out some extra time, and when you can attend next, I'll try to get another answer, another part at least. Yeah, sure. Tomorrow possible? Yeah. Okay. Then, okay, as of now, let's take it confirmed. Okay, tomorrow we'll have one class, same time. I'll try to solve. First, let me check my whether I'll be able to do something today. Right? If I get an answer, we'll definitely have. Okay, only if I don't get any solution, I will update you. Otherwise, class is confirmed. Okay, right? So as of now, let's take it class is confirmed. I'll find out some time. I'll solve at least the third part completely, right? So that we can get at least the next part done. All right. Okay. Then anything else? Any doubt from this question? I'll share you this document. What I have written, right? Uh, this document I'll share you so that you can keep it as reference and you can solve, right? I will open. I'll say I'm trying to convert this into PDF now. If it gets converted, no issue. You can simply open as a PDF. Otherwise, the tool I am using is the Microsoft. What is that? What's the name? OneNote. Microsoft OneNote. Have you heard? It's a built-in in every Windows platform. OneNote is there in this. Simply go to search and type one. You have it, right? So anyway, I'm trying to convert into PDF. It may take 1 or 2 minutes, right, to convert. As soon as that is done, I'll send it in the WhatsApp itself. Is it okay? You please download from there and refer it. Okay, that completes this second question complete. Hmm? All right. Okay, we'll meet tomorrow then. Okay. Yeah. Uh, Friday. Okay. Let me assume that I finish one more by tomorrow. So three is over. There are seven. So Friday means at least I should be able to solve three more. Maybe one, two, three. Okay, we'll see.